Why do things fall down when you drop them? When you jump up, why do you land on the ground instead of floating off into space? Of the four fundamental forces of nature, gravity is the most intuitive one. We experience gravity every second of our lives, so it makes sense that our brains are evolutionarily equipped to intuitively grasp the effects of gravity, at least here on Earth. But what is gravity exactly? How does this mysterious force work and affect the fabric of space-time? Why does it affect the very nature of the universe itself? Is the question why even a good scientific question?
Science can describe how gravity works, but can they describe why it works? So this is the how-why duality here. And in science, if we can describe how something works and predict its future behavior, we claim to understand it and we move on. You can ask deeper questions about it. Why is there gravity? What is the meaning? What is the purpose? And go ahead, but I'm good with what I've done, and I can land a spacecraft on Mars inside of a crater in a hole-in-one using my understanding of gravity, so I'm pretty good with it. So I'm not distracted by the more philosophical side of that. Why does it work?
Gravity is a natural phenomenon by which all things with mass or energy, including planets, stars, galaxies, and even light, gravitate toward one another. Modern work on gravitational theory began with the work of Galileo Galilei in the late 16th and early 17th centuries. In his famous experiment dropping balls from the Tower of Pisa, and later with careful measurements of balls rolling down inclines, Galileo showed that gravitational acceleration is the same for all objects. This contradicted Aristotle's belief that heavier objects have higher gravitational acceleration. Galileo postulated air resistance as the reason that objects with low density and a high surface area fall more slowly in an atmosphere. Galileo's work set the stage for the formulation of Newton's theory of gravity. In 1687, Sir Isaac Newton published Principia, which hypothesizes the inverse square law of universal gravitation. In Newton's own words, "I deduced that the forces which keep the planets in their orbs must be reciprocally as the squares of their distances from the centers about which they revolve, and thereby compared the force requisite to keep the moon in her orb with the force of gravity at the surface of the earth, and found them answer pretty nearly."
So Newton was deeply puzzled by how you can have something called, in which he coined the phrase, action at a distance. He wrote down the equation that worked. He wrote down the equation. The moon goes around the earth, earth goes around the sun, the moons of Jupiter go around Jupiter. He accurately described that with his equations of gravity. He said, one day I think we're gonna find some way that they're connecting to each other, but I don't know what that is right now, but I know my equations work. He called it spooky. It was spooky to him. That's his word. Spooky action at a distance. Fast forward 230 years. Get to Albert Einstein. Gravity is the curvature of space and time. And you're moving on the curvature of that fabric. That's gravity. Oh my gosh, is it even a force then? Is it even... So there's no need to think of it as an action at a distance.
Newton's theory enjoyed its greatest success when it was used to predict the existence of Neptune based on motions of Uranus that could not be accounted for by the actions of other planets. However, a discrepancy in Mercury's orbit pointed out flaws in Newton's theory. By the end of the 19th century, it was known that its orbit showed slight perturbations that could not be accounted for entirely under Newton's theory, but all searches for another planet orbiting the Sun even closer than Mercury that would account for the perturbation had been fruitless. The issue was resolved in 1915 by Albert Einstein's new theory of general relativity, which accounted for the small discrepancy in Mercury's orbit. In general relativity, gravity is described by the geometry of space-time and the laws of physics. According to general relativity, gravity is not a force, but instead is caused by the curvation of space-time caused by matter. Although Newton's theory has been superseded by Albert Einstein's general relativity, Most modern gravitational calculations are still made using Newton's theory because it is simpler to work with and it gives sufficiently accurate results for most applications involving sufficiently small masses, speeds, and energies. Perhaps the most extreme example of gravity in the known universe is a supermassive black hole, from which nothing, not even light, can escape once past the black hole's event horizon. Supermassive black holes have masses that are more than 1 million suns together. Scientists have found proof that every large galaxy contains a supermassive black hole at its center. The supermassive black hole at the center of the Milky Way galaxy is called Sagittarius A, and it has a mass equal to about 4 million suns. Although mind-boggling, such extreme mass and gravity is incomprehensible to us. We are more used to deal with the effects of gravity here on Earth, where gravity gives weight to physical objects.
So matter tells space how to curve. Space tells matter how to move. It moves along the curvature of space. You don't need an action at a distance. There is no action. It can't do anything else but do that. It's like you have a funnel and you take a ball and you roll it on the funnel. The ball can only do what that funnel tells it to do. And it'll if you give it a sideways motion, it'll start spinning around. There's no magic hand coming in there. It is following the curvature of its space-time continuum. This construct that you provided for it. So now, I can describe what gravity is doing. I even have a mechanism for it. Are you going to still ask me, why is there gravity? Is that answer not fulfilling enough to you, even in the why department? You can say, well, why would a particle curve space? You can just keep doing that. That's fine. But is there a point where you'll be satisfied with the answer? Oh, that answers my why. There's a point where it's not especially productive to continue to think about the world that way. I'm telling you, gravity really is the curvature of space and time. That gets us the Big Bang, and or energy will curve the fabric of space and time. Why does matter and energy curve the fabric of space and time? Okay, that's a frontier. We're still working on that.
The gravitational attraction of the original gaseous matter present in the universe caused it to begin coalescing and forming stars and caused the stars to group together into galaxies, so gravity is responsible for many of the large-scale structures in the universe. Gravity has an infinite range, although its effects become weaker as objects get further away. Gravity is the weakest of the 4 fundamental interactions of physics, approximately 1,038 times weaker than the strong interaction, 1,036 times weaker than the electromagnetic force, and 1,029 times weaker than the weak interaction. As a consequence, it has no significant influence at the level of subatomic particles. In contrast, it is the dominant interaction at the macroscopic scale and is the cause of the formation, shape, and trajectory of every astronomical object. An open question is whether it is possible to describe the small-scale interactions of gravity with the same framework as quantum mechanics. General relativity describes large-scale bulk properties, whereas quantum mechanics is the framework to describe the smallest-scale interactions of matter. Current models of particle physics imply that the earliest instance of gravity in the universe, possibly in the form of quantum gravity, supergravity, or a gravitational singularity, along with ordinary space and time, developed during the Planck epoch, up to 10 to 43 seconds after the Big Bang, possibly from a primeval state such as a false vacuum, quantum vacuum, or virtual particle in a currently unknown manner. Attempts to develop a theory of gravity consistent with quantum mechanics, a quantum gravity theory, which would allow gravity to be united in a common mathematical framework or a theory of everything with the other 3 fundamental interactions of physics, are a current area of research. A quantum theory of gravity would give us a much better picture of the nature of the universe, but for the moment, it still remains a physicist's dream. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this.